welcome to the class of Intelligent Product Design. In this part of the lecture, we will go into the depth of the design of control system. Okay. But first of all, let us look into the second order system that we have talked earlier, the basic representation of it and the response of the second order system, because that is very fundamental to many of our system design. So, this is the unit impulse response of a second order system. So, that means that something like this. Let us imagine that I have a mass here, okay, and I have a spring here, and there is a dash spot here like this, okay, K and C. This is a single degree of freedom system, and I can also show you that if I put a force F here, okay, and let us say x is the response at the mass m, then I can write down the free body diagram in a way that force F is coming out here, and there is an inertia force. Against that force that is applied, there is a resistance force from the spring Kx, resistance force from the damping Cx dot. So, this equation becomes what? Mx double dot plus Cx dot plus Kx equals to F, which is a function of time t. Now, let us say I carry out the Laplace transformation, then this becomes what? S square m x plus S c x. The capital X I am giving intentionally in order to say that this is a variable which is coming out of the Laplace transformation of the system. In other words, x bar is simply equals to integration 0 to infinity e to the power minus st x t dt. Okay. So, that is my x, you can call it x itself. So, not x bar, simply x, okay, capital X. So, now then I can write the transfer function, that is x over f bar is 1 over s square m plus s c plus k. Okay. So, this is, you can see that the denominator is of second order. So, this is a second order system. Now, I can also see this is the transfer function, and that tells us that x equals to, I can say f t, f bar, of course, this is f bar into 1 over s square m plus s c plus k. And this f bar, this which is the frequency domain transformations of f t, let us say that is an impulse function, something like that I just hit a system, okay, for a fraction of a second. That means something like this f t. If I try to see f and let us say at t equals to t 0, I simply give an impulse response and then it becomes 0. So, the impulse force, and so the response of the second order system with respect to this impulse force is what we are plotting here. And we can see here that if this damping constant, if this becomes equals to this 1.0, then there is almost no oscillation in the system. This is related to what we call critical damping of the system, but this critical damping we have to define here in terms of zeta, actually not the damping constant but the damping ratio, and then the damping ratio zeta is defined as C over Cc, that is C over 2 root k, and then corresponding to this value of 1, there will be no oscillation, and as the zeta value will be lower and lower, the impulse response will show lot of oscillations in the system. Now, this is an impulse response. Okay. Then what would be the typical transient response of a second order system? So, this is the way we can write the second order system. Basically, here we have done a little bit of further modification of that equation, because if you remember our earlier equation was ms square plus cs plus k, but now we have divided it by m all throughout. So, s square plus c by m s plus k by m, that is what is the denominator, and the same thing we have done on the top also. So, now what happens? We know that omega n is square root of k by m. So, which means k by m is nothing but omega n square. So, that is this term. Okay. We also know that the c by m is what I told you already, that zeta by definition is c by critical damping, which is 2 root k m. Okay. So, this definition will tell me that zeta times omega n will be nothing but c over 2 root k m into root k by m. That k will cancel. So, zeta omega n will be nothing but c by 2m. So, that means 2 zeta omega n will be nothing but c by m. So, we have a c by m here, that would become the 2 zeta omega n. That is the sort of representation of the system. And now, this system with respect to a step input, in this case, this is the response with respect to a step input, and there are the transient part of it and then the steady state part of the response of the system. Now, this response is very important for us. If I try to visualize this response in a 3-dimensional case where the damping ratio is increasing this way and this way it is omega n t and the output, then we see that as the damping ratio is closing to unity or more over damped system, we do not see these oscillations anymore, they simply stabilize. And as the damping ratio is lesser and lesser, they start to oscillate actually. So, these are typical representations, and for each of these systems we can get such representation. Now, what is important for us is that take any such time slice and then you have to define some basic 5 specifications of the system. In all, I will talk about 7 specifications, but 5 we can define through these unit step response of the system itself. What are these 5? First one is the rise time. That means, if unit step is my desired reference, then the first time, like the time required to first reach your signal to this point, is called the rise time. Some people define it against the time between 10% to 90%, particularly in Japan, but we will keep our definition as the first time you are crossing this point is this cutting with the desired level. Then the system is overshooting, so it is coming up to this point, that time we are going to call it as the peak time. So, this is our number 1 parameter, this is our number 2 parameter. Now, then once I have the peak time, the corresponding difference expressed in terms of percentage is the overshoot. So, this is my third important parameter. Then I have the overshoot, peak, rise with us. Now, I come to that when the vibration comes within a tolerable level, that particular time we are calling it as the settling time. So, this is my 4th parameter of the system. Okay. So, now we have these 4 parameters, and again there will be some more parameters that we will talk about with respect to different other constants, but 1 or 2 things we can actually get it from here, like the percentage overshoot. Okay. So, the percentage overshoot, you can see the ratio of the 2 things. In fact, this would become a function of the damping ratio of the system itself. And then the other one is the settling time, which is 4 over zeta omega n. That means, the more the natural frequency or more the damping ratio, the lesser will be the settling time for the system. Now, if I look at that with respect to the damping ratio, if you see, this is the relationship between percentage overshoot and the damping ratio. That means, percentage overshoot is only the function of the damping ratio. So, if the damping ratio increases, percentage overshoot simply comes down very fast. Okay. And if you look at the other way around, that means in terms of the change that is happening in the peak time of the system, the peak time Tp depends varies inversely with the damped natural frequency of the system. So, in that case, if the damping ratio increases, then this part decreases. If this part decreases, peak time increases. So, if the damping ratio increases, you would see this is also going to go up like this. So, that means increase of damping is good for percentage overshoot and bad for peak time. What was the peak time? I hope you remember that for a second order system, that time it took to cross this first point 1. This was the peak time. This was your TP, right. So, the first response nature of the system, that is going to worsen with the damping ratio, and whereas this overshoot is going to come down sharply if I increase the damping ratio. This is going to come down, this is going to go up. So, there must be a point of compromise of the two. So, that is a point that we have to keep in our mind. Now, the rise time I talked about, that is related to this 2.16 zeta plus 0.6 over omega n, and that is a function of the damping ratio and the omega n, both of the system. Okay. So, now with respect to these 4 parameters, if I now look at this curve, then we would see that we have these 2 important time domain representations here. One is this rise time and another is this peak time TP. Okay. So, percentage overshoot is something that is going to basically come down, it is going to improve with the increase of the damping ratio, as the damping ratio increases. But it is also true that this peak time, the peak time to reach this point is going to increase nonlinear way with respect to the increase of the damping ratio. Because you see, if the damping ratio increases, this part actually this part comes down, and if this part comes down, so the TP actually increases. So, that means that the peak time will be more and more if the damping ratio increases. That means it will behave something like this, that if the damping ratio increases, for a higher damping ratio, we would see that the overshoot will improve. So, it will come like this, like this, like this, and then come down. So, you can see the overshoot has come down from this point to this point, but the peak time has also increased. This is a problem which tells us that there must be a point of compromise between the two, between the peak time and the percentage overshoot. So, we have to choose the damping ratio such that both of them get satisfied in the system. Now, let us look at this rise time part of the scenario. That means, the first time that it is crossing this point, the connectivity is 1. So, the rise time you can see is going to reduce if the omega n increases. So, that means, if the natural frequency increases, then the rise time is going to come down, and also the rise time is going to come down if the zeta reduces. Okay. These are the cases by which you can influence the rise time of the system. So, both zeta and omega n would be responsible in terms of controlling the rise time, whereas percentage overshoots depends solely on the damping ratio of the system. Now, so far we have considered a system which does not have anything in the numerator except a constant. But if you have a first order system, if you have, let us say, a kind of a numerator polynomial of degree 1, you can say that it is equivalent to the additional 0 present in the system. Okay. So, like the roots of the denominator are the poles, and the roots of the numerator are the zeros. So, then the effect of additional 0 you would see is equivalent to the percentage overshoot that is going to add into the system. So, the system is going to behave more with damped with respect to this additional 0. So, this is a system in which you can add an additional pole and additional 0, both of them. So, that is a more complicated case of the system that you can start to think of, that how it is going to work. Now, in order to review all these things, you need a little bit of knowledge of Laplace transformation. The first one, of course, I told already the definition of it, and then corresponding to different inputs, there is a table that we have to keep in our mind, like a impulse. This is impulse. The impulse Laplace transformation is unity. The unit step, so this is unit step. So, for it is 1 over s. For the ramp, this is the ramp, it is 1 over s square, and this is called the parabolic ramp. For it is factorial 2 over s cube. Then we have things like exponential, sinusoidal, cosine, and the product of the thing. So, these are some useful Laplace transformations you have to keep in your mind. Now, our differential equation also, we have constantly used this technique earlier, like if you have a single degree of freedom system governing equation, you can use the Laplace transformation to convert it in terms of a algebraic equation of the system. And then you can also get the transfer function of the system. I have already shown you for a single degree of freedom system. I have also shown you that this transfer function can be written as 1 over ms square plus cs plus k, and if you want to find out the time domain representation, then you have to simply carry out the inverse Laplace transformation, and that will give you the time domain representation of the same system. Now, this inverse Laplace transformation, we generally do not do it through integration directly, but we take an advantage of something which is called partial fraction. So, if we have a transfer function, a generic transfer function, where the numerator is of mth order and denominator is of nth order, then I can actually carry out a partial fraction and write this in terms of the product of n roots, and these p's are the poles, and we can write the top one as the product of m zeros. So, these are the pole 0 representation then becomes useful, and that can be further used for the inverse Laplace transformation, because then the Ts can be written in terms of each of the poles, n number of poles, where Cis, the constant corresponding to that, can be found out from this relationship, and once I do it, then the final response can be written in terms of these constants. Remember, this is valid as long as you have n distinct poles in the system. Now, if the roots are complex, then the complex roots will create a complex residue in the system. So, you can actually write this whole system as s plus b over ds, and by balancing the coefficients you can get a and b of the system. Now, here is an example that suppose there is a system which is excited at t equals to 3 seconds by a step function and by a delta function at t equals to 5 seconds. Now, can you find out the response of the system, where the system properties are given to you, mass, stiffness, and damping. So, you can just try to see that how this theorem that you have learned can fit into in terms of finding out the response of this system. Now, I told you that some specifications I have given you first and some more, total 7, right? 4 I have given you earlier, and 3 more specifications I am trying to give you now, which are called the steady state error of a system. So, the steady state error refers to the long term behavior of a dynamic system. Now, the type of a system is significant in terms of this dynamic system. If a system has no pole at the origin, then it is referred to as the type 0 system. That means, if a transfer function looks something like this, let us say 1 over s into s plus some constant. So, here you have a root which is at the origin. This is typical of a type 1 system. So, that means if a transfer function is something like this 1 over s plus a into s plus b, that means it has no root at the origin. So, we will call it as a type 0 system. And if a transfer function is something like this 1 over s square into s plus c, then we will call it as a type 2 system, because it has 2 roots at the origin. Okay. So, that is how we define the type of a system. Now, type of a system is intricately related to the steady state error that can happen to a system. Well, let us have a look at it. First of all, what is the error in a system? Well, if you consider the input u to a system, okay, so you are considering input u, and then you have a summer junction plus and minus, and then let us say you have this plant directly here, which is Gs. Okay. So, you can write this input u in the frequency domain as us then, and then you take it out through a unity feedback. That means the h is 1. Okay. So, in this case, what is the error E here? Let us try to see the error E here. So, that means what is the output here? We know that this is the Cs, we usually call it, right. So, Cs is EGS, right. Okay. Now, what is the error E here then? Then error E here must be U minus EGS. Okay. That is the error E here. So, that means I can actually write this in a way that this is EG. So, that means E into 1 plus G equals to U. So, that means E equals to U over 1 plus G. That is what I have written here, that ES is US over 1 plus GS. Now, if this is what is my steady state error in the frequency domain, then there is a principle of Laplace transformation that time tends to infinity et is actually s tends to 0 of s times this transfer function. Okay. So, s times this Es, and that is s times us over 1 plus gs. Now, if I try to put s tends to 0, then how it will come out? Well, let us say the us is some constant a, then it will become a over 1 plus g0. So, that becomes our ESS. Then the Planck transfer function would be something like this, which has k number of poles in the simple poles or the roots at the origin in the system. Let us say that is a generalized representation of the Planck, m number of zeros and n number of non-simple poles in the system. So, if this is what is my Planck transfer function, then what is the G0 of the system? Well, if there is no pole at the origin, that means if it is a type 0 system, then in the GS you are going to get some finite value. So, that means G0 will be not a kind of a indefinite value, but some finite value you are going to get. So, G0 will be finite. G0 will be finite for 0 type, for type 0. So, you are going to get some error in this system. But what if there is at least one pole here? As s tends to 0, G0 when I am trying to find out, this would become infinity, and that means the error would become 0. So, which means that the steady state error corresponding to a step input will always be 0, okay, for a type 1 or a greater system. So, that is the positional constant Kp that we will use. ESS is a over 1 plus Kp, and this steady state error will be 0 for any system which is greater than or equal to 1. Now, if I try to use a ramp input, then the ramp input would be like this. Okay. In this case, it is a over SGS, which means you need to have not a type 1 system, but a type 2 system in order to vanish this. There is Kv defined as limit s tends to 0 SGS. So, that means this kV to be infinity, and in order to, because this is what would become the A over kV here, A over kV here. So, in order to have that, you must be having a system which is greater than or equal to type 2. Extending this logic, finally you can write that type 0 system is going to show infinite error for ramp and parabolic, and some finite error here in the step input. Type 1 system will show 0 error against step, but for ramp there will be finite error, infinite error against parabolic ramp. Type 2 system will be 0 here, finite here. Type 3 onwards will be all 0, which means if a system is having 3 roots at the origin, it is going to follow the signals up to parabolic ramp without any problem. Now, with this idea, we have the 7 specifications with us. One thing that can happen to a dynamic system is that many times it can actually become unstable. So, let us look into the stability of a dynamic system, which is of a deep concern, particularly if you think of a problem like this, which is the problem of a inverse pendulum problem. We call it inverse pendulum. Okay, as the cart is moving, okay, only through the movement of the cart possibly you can keep this inverse pendulum problem alive. That is this whole thing. If you remember that in our childhood, we used to actually vary our finger position in order to keep this steady. So, this is the stability of an unstable system, which is inherently it is always trying to fall down. So, that is what is an unstable system. Now, how to test the stability of a system? So, that you have, let us say you have a transfer function. How to check whether this is going to be a stable system or not? Well, one way to do it is that you check it the numerator polynomial, find out the roots of the system, and if these roots are also called the poles. So, if the poles are positive, then that means the system is going to be unstable, or if it has, even if it is complex, if it has positive real roots, the system is going to be unstable. But of course, every time for a nth order polynomial, you can carry out this factorization. So, there is a simpler method which is called the Routh stability criteria, that you can utilize to check the stability of your dynamic system. So, if your system is something like this, that your system can be written in terms of a polynomial that we have described here. That means, if you write it down here, it will be a0 s to the power n plus, that is the denominator polynomial, let us call it denominator polynomial, plus a1 s to the power n minus 1, like that it will go up to a0. Then what we can do in the s to the power n, we can construct this as a0 and then a2 every alternate terms. Okay. So, a0, a2, a4, a6, so on and so forth. N to n minus 1 will be a1 and then a3 alternate terms, so on and so forth. You are going to hit next s to the power n minus t, which has a b1 coefficient that can be constructed out of these a0, a2, a1 and a3s, etc. Now, in order to construct this row, you have to consider this one as the pivot of the row, and then every term can be defined in a way that b1 is minus of a0, a2, a1, a3, b2 is the determinant of minus of a0, a4, a1, a5 divided by a1, of course, b3 is also like that. So, this is the table that for b1, b2, b3. Like that you have to do it till the end of the series, and the Routh theorem tells us that the right half plane poles, that means unstable situation, the number of poles is equal to the sign changes in the first column of the system. So, using that you can check the stability of the system. Okay, this is where we end this lecture, and then we will talk about the root locus part of it, that where does the roots go. Thank you.